Hello everyone, my name is Naya and today I will be presenting the Constant Velocity Lab. The main objective of this lab was to observe an object, or in my case a spherical ornament, moving at a constant velocity in one dimension. Another objective was to use Newton's second law to make predictions about the ornament's position at different times. So key concepts and equations in this lab. Velocity is defined as the change in position or displacement over a particular time interval, while Newton's second law explains the idea that change in velocity, otherwise known as acceleration, is proportional to the net force. So when the net force is zero, an object has constant velocity. Some key equations for this lab include the position update and velocity update formulas as shown in this slide. So experimental setup. The object I chose to observe was a red ornament because its color made it easily distinguishable from the surroundings. Its surface was smooth and it was spherical in shape, ensuring that it would roll on the tabletop smoothly. I was able to find the mass of the ornament online and made sure to measure its diameter so that I could use it as a reference length and tracker. I also chose to orient the horizontal axis so that the positive x direction was to the right. Here is a shortened video of my experiment that I uploaded to Tracker. I had to cut out the first few seconds of the video because it contained the portion where the velocity of the ornament was increasing due to the initial push I gave it. After trimming the video, I made sure to mark the position of the ornament after each 0.033 second frame by placing a red diamond in the center of the ornament each time. This ensured that Tracker was able to generate a table and graph with accurate position versus time data. And, as you can see, the position versus time graph Tracker generated had a constant slope, indicating that the ornament was moving at a constant velocity. So, data collected. From the data table in Tracker, I was able to determine initial conditions like start time and the initial position of the ornament. I also used the position versus time data generated by Tracker to determine the position of the ornament at 0.033 seconds and therefore calculate its initial velocity as shown on the right side of the slide. Because there was no net force acting on the ornament, the initial and final velocity of the ornament were the same, so I didn't need to calculate final velocity. This is a computational model of the ornament's motion using GlowScript starter code that I made minor changes to. So in the red box to the left, you can see that I ended up changing ball.m, or the ornament's mass, to 0.02835 kilograms, ball.pos to the initial position of the ornament up to the value Tracker provided me, and ball.vel to the initial velocity that I was able to calculate earlier on. And then on the box to the right, I changed the Fnet to 000 because the net force on the ornament was 0, and it was not accelerating. So essentially, the whole point of the code in the red box to the right was to update position and time in 0.01 second increments so that GlowScript could create a table of data for the ornament's position at different times and a position versus time curve. So here is a video of the program running in GlowScript. As you can see, the position versus time graph generated had a constant slope, indicating that the ornament should have a constant velocity. I made sure to graph the position versus time data retrieved experimentally from Tracker and computationally from GlowScript on one graph using an Excel spreadsheet. The lines basically have the same slope and y-intercept, indicating that the computational model predicted the experimental results well. However, it is likely that the slope for the experiment data curve is slightly higher because I may not have placed the red diamonds on the ornament on the exact center of it in Tracker. I could have improved this by making sure to place tape on the ornament before starting the experiment to clearly denote the center of it. So if the axes are flipped so that the ornament was traveling in the negative x direction, the slope of the position versus time graph would have the same magnitude but opposite sign, and the initial position would remain the same. So essentially, the green curve illustrates what the position versus time curve would look like if the axes were indeed flipped. So it's not really possible to say how many forces are acting on the ornament because Newton's laws of motion can only be used to determine the net force. We know that a normal force and gravity force were acting in the positive y direction and negative y direction respectively, but we don't know how many forces like air resistance and friction were acting in the x direction. However, it can be assumed that these forces were quite negligible though because the ornament had constant velocity. Thank you for watching!